Okay, so our directions are just going to tell us to simplify. And then remember a couple things that we talked about from our first set of notes. We said if we can't take the square root of a number, is it possible to find factors that we could take a square root of? So what we could do is try to take the square root of the factors of that number. And so you guys did that a lot last night on the homework, a little bit on the first homework. And then the one that's going to apply more to us today with the quotients is if you have the square root of a fraction and you can't take its square root, try to break it into the square root of the numerator over the square root of the denominator. So you'll also see us do that today in the practice. So I've got a lot of different problems. They range from easy to hard, and it just kind of depends on the problem. So let's start with a little easy. Now I'm going to obviously be showing you a little bit more than what I would be seeing, because I want you guys to be able to see where did that come from, those of you who are struggling with understanding it. But on homework, a lot of this can be done in your head. So I'll explain, this I have to see, this I have to see, this could be optional. So because they're both radicals, I can put them underneath one radical and do the multiplication. So instead of radical 2 times radical 20, I could say it's the radical of 2 times 20. Well, the square root of 2 times 20 would be the square root of 40. So minimally, original problem, second thing I would see was radical 40. Now you need to break 40 into perfect square factors. So what's this perfect square factor of 40?
4. 10.
And its partner would be 10. So now what we're going to do is take the square root of each of those. So square root of 4 is 2, and I can't take the square root of 10, so I just leave it as the square root of 10. So the answer is 2 radical 10. Okay, so that's pretty straightforward. All right, let's try another one. We're going to get a little bit more complicated. What if we have coefficients? How do we handle that? So we have 3 radical 8 times 5 radical 2. And you need to keep the premise of outside goes with outside, inside goes with inside. So I can multiply coefficients together, and I can multiply radicands together, but I can't multiply a coefficient and a radicand. So in other words, oops. Meant to change colors, he didn't change. I can multiply the 3 times the 5. Because they are both coefficients. And then I can multiply radicands. So that would be 8 times 2. And then we just keep doing math. So we get 15 radical 16. And then we check to see, we have to follow the simplest radical form rules, SRF rules. Can I do the square root of 16? And the answer is yes, you can. So square root of 16 is 4. And that would give us 60. So the colored step is really an optional step. The rest of it you should be showing me. All right, let's put in your favorites. What if your radicals had fractions in them? So square root of 3/20 times the square root of 1, and 2/3. So not just a fraction, but a mixed number as well. Well, they're both radicands, which means I can put them underneath one radical. But you would never catch me trying to multiply a fraction and a mixed number. We need to only multiply fractions. Oops. So what would I get if I changed 1 2/3 to an improper fraction? 5/3. So what I'm going to try to do is to simplify this problem before multiplying. And if you notice, 3 goes into itself once and into itself once. And then 5 goes into itself once and into 24 times. So what you're left with is the square root of 1 times 1 over 4 times 1. Now, we talked about how we can just look at it as the square root of 1 over the square root of 4. What's the square root of 1?
1.
And the square root of 4?
2.
and that all comes outside. So the answer worked out to be 1/2. Okay. All right, let's try another one. So now we're going to kind of go back to chapter 5 a little bit when we were multiplying monomials and binomials and things like that. What if you were asked to square 2 radical 7? So I'm going to show you 2 ways to do this, because we talked about doing this 2 ways. Way 1 would be to expand this, and that means write the 2 radical 7 as many times as the exponent tells you. So we would write 2 radical 7 times 2 radical 7. And then this ends up looking like example 2, where we're going to end up multiplying the coefficients together. And we get 2 times 2 is 4. And then we're going to multiply the radicals together. And we get the radical of 49. Now, a lot of people are already to the point where they say, hey, if I multiply radical 7 by radical 7, I just get 7. Okay, if you're there, that's fantastic. If you're not, hold on, you'll get there. So at this point, I have 4, and the square root of 49 is 7. And 4 times 7 is 28. Okay? All right, here's another little blast to the chapter 5 past. What if I have square root of 5 times the quantity? Square root of 5 minus the square root of 10. So what am I going to do to solve this problem? What's my initial step, Lily?
Distribute.
Yep, we got to distribute. That's always the first thing. If we want to get rid of parentheses, is we're going to distribute. So the first problem is going to have us multiplying radical 5 times radical 5. And then it says minus, so I put in minus. And then I'm going to distribute the radical 5 times the 10. So that's going to give me radical 5 times radical 10. All right, let's hope we're all at the stage now. What do I get when I multiply radical 5 times radical 5?
5.
I just get 5. I don't have to say radical 25. I know it's going to be 5. Over here, though, it's not the same case. So I multiply 5 times 10, and I get the square root of 50. All right, now I have to see if I can simplify, going back to rule 1 of my SRF rules, and what's the greatest common factor, or greatest perfect square factor of 50? So 25 and his partner would be 2. So I'm going to go ahead and take the square roots of those. So I still have 5 minus square root of 25 is 5, and I can't really do anything about the square root of 2. Now, can I simplify that problem? Can I combine them? And the answer is, this is kind of like saying 5 minus 5x. Can I combine 5 minus 5x? No, they're not like terms. So if radicands don't match, then you can't really do anything with coefficients, so you're done. Actually, that's what we're going to be talking about tomorrow, is adding and subtracting radicals. Okay. Let's see, I think I'm going to go on the next page for the next one. So let's, as Emerald likes to say, let's kick it up a notch. Let's take that problem, but instead of just distributing a coefficient, let's distribute a variable as well. So we got radical 2x times the quantity radical 8x minus 3, oh, there's a coefficient, radical 12x squared. So we're still going to distribute. Now this one I'm going to do a little piecemeal, so step by step. So this one we're going to have 2x times 8x. And then we're going to write minus, and then the 3's out in front, so the 3's still going to be out in front. And then in the radical, we're going to have 2x times 12x squared. Okay? So the first one, 2 times 8 is 16, x times x, x squared, minus 3. 2 times 12 is 24, x times x squared. We add the exponents, we get x cubed. Oh, look at how nice the first one is. What's the square root of 16x squared? Yeah, square root of 16 is 4, square root of x squared is x. Next one, not so pretty. Perfect square factor of 24 would be?
6 and 4.
4 is the perfect square factor, 6 is his partner. How would I split x cubed so I could take square roots? I always pull out 1. That leaves me the greatest even amount left over. So I have x squared and x. And again, if you notice my pattern, the number I can take the square root of, I write on the left. The number I can't take the square root of, I write on the right. And that's just the pattern I follow all the time, and it helps me keep things straight. Okay, so we still have minus, we still have 3, and now we can do square roots. So the square root of 4 is 2, and that comes out here. The square root of x squared is x, and that comes out here. The 2 I can't take the square root of, the 6 and the x. When I take their square roots, they're just going to remain under a square root symbol. So we just go ahead and simplify, and we get 4x minus 6x times radical 6x. Now could I combine those guys? And the answer is no, because I still have one of them with a radical attached to it. So we're done. Okay. So speaking of done, let's move on to quotients. We've done enough with the products. So let's just talk about some different ways we're going to approach fraction problems. So this one I've got a square root of 15 over square root of 3. And I can't take the square root of either one of them. So one of your options is to try writing it as a single fraction and see if there's anything that you could do to simplify that fraction. And what you should notice is they both have a 3 in common. So 3 goes into itself once and into 15 5 times. So really what you're doing is taking the square root of 5, which you can't, so you're done. Okay? So instead of breaking it into numerator and denominator, that didn't help me, so putting it back as a fraction is what did help me on this problem. All right, let's look at another one similar to that. So again, I have an issue of neither one of these are perfect squares. So I'm going to first try putting it together as a single fraction and seeing if there's something that I can simplify by. So what can I simplify 8 and 72 by? What do they have in common? No, 9 can't go into 8. 8 can go into 8, and it can go into 72 9 times. Got to be careful what you say versus what you mean, right? So then we have the square root of 1/9. What kind of numbers do we have now? Perfect squares. So this is going to be a piece of cake. Square root of 1 is 1. Square root of 9 is 3. And there we're done. Okay. All right, let's complicate it more because we love to do that. Number 9, we've got 21 radical 48 over 7 radical 3. So what's different about this problem is I have coefficients and I have radicals. So what I'm going to do is split this into 2 fractions. Let's split it into a coefficient fraction, and let's split it into, actually let's make this bigger, since 48 and 3 aren't perfect squares, the square root of 48 thirds. So 21 divided by 7 is easy. What's that? That's just a 3. Now, what about common factors in this other side? 4 and 8 add up to what? 12. So according to divisibility rules, 3 can go into that number. So I'm going to divide each of these by 3. So 3 goes into itself once and into 48 16 times. Ooh, bingo, bingo. So I've got 3 square root of 16. But what's the square root of 16? And then we have 3 times 4 is 12. And there's your answer. All right, so that third rule is the one we're going to practice now. We've got 2/3. I cannot simplify it. It's as simplified as it can get. So our next option is to try to take the square root of the numerator and square root of the denominator. The problem is I can't take the square root of 2 or 3. So now what I need to do is come up with a way of getting rid of the radical in the denominator, which is our rule number 3. Okay, no radicals allowed in the denominator. So what we talked about earlier in the notes is if we multiply numerator and denominator by radical 3, I'm actually just multiplying by 1, so I'm not changing a value. I'm just changing its appearance. It's like if somebody goes on a diet, they don't change who they are, they just change how they look. Okay? So then we have 2 radicals, so I can multiply 2 times 3, and I get radical 6, and then I have radical 3 times itself gives me 3. Now, can I simplify that?
Yes.
I'm hearing yeses and nos. Okay. Dakota, tell me why no.
Well, because it's a radical in the numerator, which is allowance.
We can have a radical in the numerator, so I don't have to do anything more in that respect, but my question was, can I simplify? Can I reduce? Because I've got a 6 and a 3, and I'm just itching to take it down to 2. But the problem, there is a problem here. John, what's the problem? We've got a radical around the 6, and we have nothing around the 3. That means 3 is an outside number, 6 is an inside number, and they don't communicate with each other. So this is actually the answer right here. Now, remember, the book may pull out the coefficient and put the square root opposite the fraction bar. So that's another option for writing that answer. All right, we've got 2 more. We've got 15 over radical 5. So this one I can't rewrite as a fraction. Ethan, you're supposed to be taking notes, not just watching. This is not an observation class. We can't just simplify because, again, we have the same situation as last problem. We have an outside number and an inside number, so we can't communicate. So the only thing I can do is follow rule number 3 and get rid of the radical in the denominator. So what am I going to do to get rid of the radical in the denominator? I'm going to multiply top and bottom by radical 5. So what that gives me now on top is a 15 radical 5, and on the bottom, radical 5 times itself is 5. Am I done?
No.
Okay, why not? What do I have that I can do? So notice now I have a 15 and a 5 that are outside numbers, so this guy and this guy. So I can reduce both by 5. So my answer is 3 radical 5. Okay, I've got one more, and this one's the doozy, because it's going to have your favorite kind of number in it. Fractions. I heard somebody already say fractions. So I have 1/3 radical 1 1/4 times 1/4 radical 3/10. So we did a problem similar to this. And what we said is we can multiply outside with outside. So we're going to get the 1/3 times the 1/4. And then we're going to multiply radicands. So we'll have 1 1/4 times 3/10. So the issue becomes we can't do the multiplication inside the radical with that mixed number. But I can take care of the outside pretty easily, and I get 1/12. So inside, I'm going to change 1 1/4 to 5/4, and then try to multiply it by 3/10. So if you notice, 5 and 10 have a 5 in common. So I simplify by reducing by that value of 5. And I get 1/12 times radical 3/8. But we have a problem. The 1/12 is cool. There's no issues with him whatsoever. It's the radical 3/8. So I'm going to take a moment, go over here, and let's deal with that radical 3/8. So what we said is if you cannot take the square root of the fraction, maybe you can try to take the square root of the numerator and the square root of the denominator. But then that leaves us, since 8 isn't a perfect square, it leaves us with a radical in the denominator. So there's 2 options how to handle this problem. First option, multiply top and bottom by radical 8. So at this point, we get radical 24 over 8. But we still have a problem. We broke rule number 1 because there is a perfect square factor of 24. What's the perfect square factor of 24? 4, and his partner would be 6. So when I take the square root of 4, I get 2, I cannot take the square root of 6, and then I have over 8. But yet, we're not done. Why? Who can talk to each other? The 2 and the 8. 2 goes into itself once and into 8 4 times. So now we're ready to go back and rejoin this problem, where we have 1/12 times radical 6 over 4. We multiply straight across since there's nothing left to reduce, and we get radical 6 over 48. And again, radical and the inside-outside numbers can't communicate, so that's as far as the answer can go. Now, I'm going to give you a second option to solving this problem. Some people like to try to simplify the denominator. What's a perfect square factor of 8? Okay. So keeping that in mind, we get radical 3, square root of 4 is 2, and I can't take the square root of 2. Now what would I be multiplying top and bottom by? I'd be multiplying top and bottom by radical 2, which would give me radical 6 over 2 times 2, or radical 6 over 4. Now, what's the difference here? Well, I'm going to give you a problem that you've done before. That there's two ways to solve multiplying fractions. Way one is just to multiply straight across. So we get 12 times 15. We get 10, 30, placeholder 5, 1 for a total of 180. And then we have 16 times 18. So we get 48, 108, placeholder 8, 1. Shh. I'm trying to teach here. Over 288. The problem then becomes you have very large numbers, and now you have to try to find common factors. So what's the common factor of 180 and 288? We'll be here for a long time if we start with that. But there we go. That goes in once, 4 and 4. Now what? 9. We're not going to go 2. So 9 goes into 14 once with 5 left over, and 9 goes into 54 6 times. Now I can do another 2. And I get 5/8. Or I can be smart and say, hey, 12 has a 4 in it, so when I divide out of 4, or it has a 6 in it, divide out of 6, I get a 2. Divide 6 out of 18, I get a 3. 3 goes into itself once and into 15 5 times. 2 goes into itself once and into 16 8 times. And I'm left with 1 times 5 is 5, and 8 times 1 is 8. That's the difference. Guys, I'm sorry, we're not supposed to be fooling around right now. Athena. Okay? That's the difference between these two strategies. Do you simplify first, then multiply, or do you multiply and then simplify? So it's up to you to decide how you want to do that. Okay?